Hello everyone, I am Massimiliano and this is Open World Compositional Zero-Shot Learning, a joint work with Ferjat, Yonchin and Zeynep. The goal of Compositional Zero-Shot Learning is to learn a model able to recognize the object and the state present in an image. To do so, we are given a training set with some compositions of objects and state of interest, and at this time, we want to classify both seen and unseen compositions of the same objects and states. There is a problem though with this setting, which is the assumption that the unseen compositions we will face at this time are known a priori. This is limiting since the model will actually exclude from the out space compositions which may exist in the real world, such as dry apple, and we will not be able to then recognize these compositions anymore. It is clear that for any model applied in practical scenarios, we cannot impose such optimistic constraint on the output space. This is why in this paper we propose to remove the closed-world boundaries of the standard setting, focusing on the more challenging open-world setup, where we impose no constraints on the output space of the model. Note that this implies two things. The first is that the output space now gets very, very large, spanning all possible combinations of objects and states. Second, there are also less feasible compositions that are rarely or never found in the real world, but that can act as distractors and harm the performance of our models, and we should take them into account while developing our systems. To address this problem, we start with a simple approach for the closed-world scenario, which we name Compositional Cosine Logics, or CompCos. The approach first projects an image into a shared embedding space. Then it takes the objects and states, extracts embeddings for them, and the function composes these primitives to get the embeddings for each composition. We then compute the cosine similarity between the image and the composition embeddings, and we use these cosine similarities as class scores for our cross-entropy loss. Now, this works in the closed-world scenario, but in the open-world setting, the presence of a large number of unseen compositions may change the decision boundaries and make the model output wrong predictions. To tackle this issue, we assume to have feasibility scores associated with each composition. Now we can use the feasibility scores to just filter out from the output space every composition for which the feasibility score is below a certain threshold, or, in a softer manner, we can use these scores as margins in the loss function. In particular, we subtract the feasibility scores from the cosine similarity, and thus the more a composition is feasible, and the less its embedding will be penalized by the loss, and vice versa. But how do we estimate the feasibility scores? Well, the idea is pretty simple. If two objects are similar, it is likely that they share the same states. We can then exploit the available training compositions and the primitive embeddings to estimate the feasibility scores. In particular, given an unseen composition such as wet tomato, we look at which objects in the dataset appear with the same state. In this case, we see that both dog and apple have the state wet. Since tomatoes are visually similar to apples, we can conclude that tomatoes can be wet, and we associate a feasibility score for wet tomato that is the cosine similarity between tomato and apple embeddings. Obviously, we can have cases where the query object is pretty dissimilar from the ones in the training set that are associated with that state. This is an example, for instance, with ripe dog. And in this case, we have a low cosine similarity among dog and tomato, and thus a low feasibility score. Note that since if two states are similar, it is likely that they can be applied to the same objects. We apply the same process also from the point of view of the states, and we average the scores to get the final estimate. Going to the results, our model works pretty well in the closed-world setting, surpassing the state-of-the-art SimNet by 1.5 points in AOC in the challenging mid-states benchmark. And things get even more interesting in the open-world setting, where every method loses performance, but our CompCos still doubles the performance of the best competitors in terms of AUC on mid-states. Note that the original mid-states has 400 unseen compositions at this time, but we consider an output space of almost 30,000 compositions in the open-world setting. Here you can see some funny qualitative results where our closed-world model mistakes a brown pie for a rusty pie and a huge balloon for inflated eggs. You can check the paper for more results and ablation studies. Thank you, and I hope to see you at the conference.